Good day, class. Let's try solving some sample problems naman para ma-appreciate niyo yung concepts and yung equations behind kinematics that we discussed. I understand I left some of them blank in the lecture video, but if you would see, some of them really matches yung lecture workbook. So if you read the workbook, you probably know how to solve it. If you did, thank you so much. At least you've read through the equations there, and you pretty much the succeeding problems in the future will be just a variations of those lang naman eh. It really just here to test how you would use it and how you would decide which equation to use. Let's try for sample number 1. It's simple enough. We're here to find the displacement and average velocity. We're here to define the displacement and velocity, average velocity of a moving car between positions A to F. We are given to the table here. And the best thing we can do actually is position them graphically, or you can also make use of the table now. As we recall in our previous exercise, if you would recall, the total displacement is simply just the final position. Is just just the difference between the final position and the initial position. In this case, we're asked to look for the displacement of A to F. So that will be the final position, that will be at F, and the initial position that will be at A. Substituting the values, we'll get negative 53 minus 30 meters, where your displacement is negative 83 meters, or 83 meters opposite to your reference point. Same with the average velocity. Now that we have the delta x, average velocity is simply the change in position or displacement over a time interval. In this case, the change in displacement between the change in position between between A and F is just negative 83 meters, and the time elapsed there is from 0 to 50 seconds. So we would yield the answer of negative. You would get at least 1.66 meters per second. Okay, moving forward, we have another problem, sample number 2. Here we are already given several units already. We have a displacement of 20 meters at time elapsed 4 seconds. We are asked to find what is the runner's velocity, and B, should he continue after the 20-meter point, So the coach already stopped his clock watch. What is his position after 10 seconds have passed? Let's go with A. With A, it's pretty much simple. We have a clue here. The clue here being that the runner is described as having a constant rate. It's running along a straight line at a constant rate. So this gives you an idea that we are at a constant velocity condition, giving us the formula that delta x, meaning that our instantaneous velocity and our average velocity is equal to delta x over delta t, which give us 20 over 4, that's 5 meters per second. Now for B, we can solve this live. We are asked to solve what happens if he moves way past the 20-meter mark. We're being asked what is the final position at t elapse of 10 seconds. Since we know that this is a constant velocity condition, we can use the formula xf equals xi plus bx delta t. Now substituting the values, we know that my frame of reference here is from point 20, so that will be my origin, and it's just being asked how far from that point 20 mark. So my initial position here is 0. X here would now be at a constant velocity of 5 meters per second, given a total elapsed time of t, 10 seconds. So that's 10 minus 0 at that 20-point mark. We will get 50 meters per second. The next problem. So under sample problem T, there's a combination of instantaneous velocity, average velocity. And this is a good particular problem from the book of survey. When identifying how to solve velocities asking at a particular point in time or instantaneous velocity per se. So we are given the following with an expression of x equals to negative 4t plus 2t squared. And as from the graph, it is a parabola where x here is in meters, t is in seconds. We are asked to determine the displacement at time 0 to t equals 0 seconds to 1 second, and then the displacement at from 1 second to 3 seconds. Now, for us to do that, we have to know several things. We need to know the positions at 0, 1, 2, and 3 seconds even. I plotted the equation like so, and simply just plotting in the equation the given expression, substituting the given time to the given expression or equation, we would get the positions of A, B, C, and D. And once we acquire all those, we can now get now for our total displacement. Note that you can also check our position against the position time graph to see if it makes sense or if it graphically makes sense. In this case, at t0, your position as 0. At t equals 1, you are at negative 2 meters. That's good. At t equals 2 seconds, you are at 0, so you are here. And at t equals 3, you are at 6 meters here. Okay, proceeding to solve for delta x, it's simply the change in position, so final minus initial. So in this case, the displacement for 0 to 1 second will be the final position at the 1 second and the final position at the 0 second. And the position at the 0 second, so that will be negative 2 plus 0, yielding you at 2 meters, and the following one at 1 to 3 will be 8 meters. The next question is finding the average velocity. Since we already acquired the delta x, it's simply a matter of solving for px average equals to delta x over delta t. We substitute that, and their corresponding time interval, so negative 2 over 1 will be negative 2 meters per second. And the other one, for 1 to 3 seconds, that will be 8 over 2, giving you 4 meters per second. The last part is the problem is asking you what is the instantaneous velocity? What's the velocity? Often you would hear, what's the velocity at a particular time t, or in this case, 2.5 seconds. So for you to solve this, and like we derived it before, if you understood it in the lecture, the instantaneous velocity is to get instantaneous velocity, you must get the derivative. It is simply the derivative of change in position with respect to time. In this case, you just derive this equation. So we have here x equals negative 4t plus 2t raised to 2. The x prime of it equals the instantaneous velocity, yielding you negative 4 plus 4t. Now we substitute 2.5 seconds here, and we will give us 6 meters per second. I want to stop for a bit and see that the big difference between the average and the instantaneous velocity. Average velocity, as you would graph it, yields a straight line. You're skipping a lot of points there, leaving you a lot of errors, or you're just getting the entire average of it. But if you're getting per line, per point in the curve, you would see that the values really differ by that much. All right, it's kind of cramped, but we'll make do. So there we go. Let's try a similar problem. for this is sample number 4. And it's similar to number 3, but the only difference here right now, we're talking about acceleration and instantaneous acceleration. So we are given a equation, v sub x equals to 4 minus 5t squared. It is also a parabola, if you would graph it. Since it's negative, probably pointing downward. You already have an idea now how the v curve is with relation to acceleration. But that's a topic for another day. So we're asked to find the average acceleration for the time interval between t equals 0 and t equals 2 seconds. And we are also asked the acceleration at the 2-second mark. So meaning the instantaneous acceleration at the 2-second mark. Recall that we have that average acceleration is simply the change in velocity per time interval. It can be written as the final velocity minus initial velocity, the final, the initial. Now, to simplify, given that equation, we ought to know what is Vfx and minus what is your initial and final velocity. And to get those, you just simply substitute the corresponding time interval, t0 and t2, to the equation, to the provided equation. So you would have the answers as 40 meters per second for velocity at t0 and the 20 meters per second velocity at the 2 seconds. Once you know that, you substitute then those values to get your average acceleration, and you will yield negative 10 meters per second squared. Now, to get the instantaneous velocity, just like we did with sample problem number 3, we just get the derivative of the provided equation Vx equals 4t minus 5t squared. You get that dvx dt, v prime t is also ax. You will get 0 minus 10t. Then we substitute the time provided, which is t equals 2 seconds. You get negative 20 meters per second squared. If you have questions, feel free to email me and compile them if you have as a group. Preferably, you deal with things as a group so that you can pick the equation one by one or parts of the problem one by one. And eventually, you get used to it solving individually as well. Moving to the next problem, now we're gonna deal with, say you have, what if you're dealing with two objects about to move in parallel in the same direction, but on two different roads, you know. Say you have toy A, you're given here a toy car set rolling on a straight track with an initial position of 15 centimeters. We have an initial time 0 and the initial velocity at negative 3.5 centimeters per second, and an acceleration, constant acceleration already provided at 2.4 centimeters per second squared, where A is constant. Toy B, on the other hand, is simply, it has an initial position of 10 centimeters with a constant acceleration of 0, meaning our initial velocity here is our velocity for toy B here is constant. Remember, when you have a constant acceleration, your velocity just varies linearly. But when you have a 0 acceleration or 0 constant acceleration, your velocity here now would be constant all throughout, kind of like a straight line. Okay, we are being asked at what time, if any, do the cars have equal speed? So let's just name that as t equal. And then next one is, what are their speed at that particular time? Let's name that as VE. And at what time do the cars pass each other? Okay, let's solve it one by one. Now, there's a trick here. There's a lot of variables here, but let's deal with the problem one by one. Let's first deal with A. We're being asked with T. We know very well that the time that's being asked is one more condition, that both velocities are going to be equal. So, and we're dealing with toy A at constant acceleration, where we know that the formula is Vf equals to Vi plus Axt. We substitute that, and that'll be our equation 1. Now for toy B, it's simply at constant velocity, but still we can use the same formula, VFVI equals VI plus AXT. But in this case, our acceleration, constant acceleration here is 0, yielding that, and that'll be equation 2. In fact, we already got the V, but we can test that later. So we arrange the equation to find T, and then we will get TE is equal to 3.75 seconds. Now, to get T, you simply just substitute the equation to your toy A, or simply, we already found out that VE is also 5.5 centimeters per second already, since toy B has a constant velocity anyway. I hope that's understood. If you don't like that, the easy part, you can simply substitute this to your equation 1. Okay, and the last part here is at what time they would pass. So for here, some kind of hint again, to know the equation to use, we should try identifying what is unknown, or what are the unknown, and what are the given for that particular problem. In this case, we're trying to identify time. And in this case, we also have to think that if they're gonna pass each other, they must have the same final displacement, so to speak. And we can use the particular equations for constant acceleration and at constant velocity for identifying toy A and toy B's final displacement. For toy A, we use the equation xfxi, final position equals to the sums of initial position, the product of initial velocity and time, and the axt squared over 2. We simply substitute that, and then we will have our equation 1, like so. For toy B, acceleration, again, like I said earlier, constant acceleration is 0, making it a constant velocity condition. Hence, we can make use our standard formula for constant velocity in finding final positions, which is x sub bf equals to the sum of xbi and the product of velocity toy B, constant velocity, times time. And VB is equals to V, which is we know at 5.5 meters per second. Simplifying the equation, we get this. Now we have two equations now, and we simply rearrange it, and we will arrive with a quadratic equation. Now, there are two ways to solve this. Either you solve this manually by the quadratic formula, or you simply use your high-end scientific calculator using the equation EQN function. I did the quadratic equation just to show to you. Now, obviously, when you're solving for a quadratic equation, you now solve for two roots, and you have to identify whether they're both roots or one or the other roots is real or not. In this case, both roots is positive 6.9 seconds and 0.604 seconds. This translates that the cars A and B, toy cars A and B, will pass twice at 0.604 seconds and at 6.90 seconds. This is a circular path anyway. Questions? If you have any questions, do compile them and try to and try to be specific on what part of the questions you are. Depending on what time of the day you ask my question, I can give you a call too and show to you manually how it's done, or simply just give you a clue. Okay, we have 3 more problems. Let's go with sample problem number 6. Okay, a different kind of one-dimensional problem, one motions in one dimension, but this time we're talking about vertical. Recall that for free-falling objects or for motions along the vertical axis, we're using from x-axis notation to y-axis notation, and our constant acceleration here is g. Remember to assume air resistance is negligible and gravity uh, changes in gravity per latitude is negligible as well. Okay, focusing on the problem, we're given a stone is thrown from the top of a building and is given an initial velocity of 20 meters per second. And we already have our g at 9.8066 meters per second squared. Just let me use the 9.066. Your workbook would use 9.8, I think, but that's fine for me if it's close enough. Okay, the stone is launched 50 meters above the ground, and the stone just misses the edge on its way down. We are to find the following. Okay, let's deal with them one by one. First one is at initial time 0 second. Determine the time required to reach the maximum height. So we're being asked to find T max, so to speak, when the stone has max height. And if you're gonna dissect that, at max height, you know very well that your final velocity would be 0. You know that your g is 9.8066, which is negative. And you know you are at constant acceleration. So we can make use of this formula. Vyf equals to Vyi minus gt, where g is your constant acceleration due to gravity. Okay, substituting the values that you have already, your final velocity is 0. Vyi is 20 minus 9.8066 times t. Rearranging the equation, you would get the answer t equals to t 2.039 seconds. About 2 seconds, 2.04. Okay. The next problem is, so at that particular time, what is the max height? In this case, what is the vertical max height when a stone is thrown at the 50-meter mark? So to imagine that, I mean, we can draw about it. We simply have, this is 50 meters. Say you have, yeah, this is 50 meters. Let me do that again. This is the ground, this is the height. And you're trying to find this one. The max height, or H max, so to speak. So you started here, so that will be your, technically at the 50-meter mark, that will be your Y initial, and you're trying to find this one. Okay. So we are under at constant acceleration, so constant g. So we use the formula. We already have the initial position. We already know what your launching velocity is. And we already know time. And all we have to do now is just substitute values. So I make use of the formula given all the present variables here to identify the unknown, which is your YF. Substituting the values will give you 70.271 centimeters. Meters. Yeah. meters. Consequently, there's like any math problem, as long as it's permissible, it is allowed, you can solve a problem with more than with two or more solutions actually, given that they're allowed. Okay, so you can actually solve it using also this particular formula, whereby your final velocity is equal to your initial velocity minus 2g and delta y, and you simply rearrange the equation and you will get yf. Okay, the next problem is C. Now we're being asked, what is the velocity upon reaching the height it was thrown? So from its max height, it's gonna go back to the point where it was thrown. I made an illustration here just to imagine how it goes. So you started here, and for the first part, it went here. Now we're trying to ask this part. So from this point on, you will now make use of these systems here. So your previous final velocity is 0 is now your initial velocity going down. So that will be 0. And then we're being asked what is your final velocity, which was your previous initial velocity. Without solving the equation, you already know what the you will already know what the answer is. And I will predict it's 20 meters per second, but just going downwards. So it is subjected to the same gravity too. But it's best to prove it in math. And of course, your y, it's still pretty much the same. We already have all the values. We just need to set its frame of reference. So this time, this is your frame of reference. And you have your initial position and your final position here. And to get that, we simply just subtract it, and you will get 20.271 meters. And your initial position here is actually 0 naman. Okay? Now, having all those parameters in your hand now, you can make use of these following formulas to solve for your final velocity. Y2, because you have two unknowns at that. You cannot simply assume that the time to reach it is the same as here, going down. So just to be safe, we just make use of our equations here. Simplifying this equation would give you this our equation 1, 9.8066 times t. And then you go here, you simplify here to get it in terms of t. You would get the time at 2.03 seconds. There's a slight variance than the 2.0439. From here, you substitute now the time to your first equation, and you would get a negative 19.9 or almost negative 20 meters per second. I hope that's easy to understand and to follow. All right. Okay. So motions in two dimensions. So we're going back again with our basics with vector quantities, but this time with moving displacement and velocity with respect to time. And most of the problems here are in equation form. Most of the answers here are mostly in equation form because and usually they're derived with respect to time, so that you know what are the positions of both x and y and their velocities at the same time at any given point in time. So let's take a look at this problem. Say we have a particle moving in an xy plane starting from the origin at t equals 0. We have an initial velocity of 20 meters per second in the x component and a initial velocity of negative 15 meters per second in the y component. The particle experienced an acceleration in the x direction at ax equals to 4.0 meters per second squared. We are not given an ay, so we can just assume that is 0. Let's just put that down. we are asked to determine the total velocity vector, the angle of the velocity vector, and the velocity of the particle at t 5 seconds, and the resultant, basically. Hey, there we go. So the x and y coordinates of a particle at any time t, and its position vector at this time. Okay, if you would recall our lecture, you know that we can use already the equation to solve for a, such that the total velocity vector is given in this particular expression, v sub xi plus axt I plus the products of the sums of vya and ayt and j. Again, I and j indicating the unitless vectors, indicating the x and y components. Oops. Okay. Now, you substitute what's given, and you would have this particular equation. Simplify it, and you would yield this expression. For B, you're being asked the angle at which the velocity max with the x-axis and the velocity at the of the particle at time t equals 5 seconds. So remember what we did with A, we simply substitute the time from A to have the expressions to be able to simplify the to solve for B, we simply substitute the time at 5.0 seconds. Okay, correction. This is 5.0 seconds. So to solve for B, we simply substitute the provided time at 5 seconds from our A expression. And you would yield with the following velocities for x and y. And if you recall, the VXF, the I component is the x component and the j is the y component. So 40 here is simply your 40 meters per second at x component, and your Vy is negative 15 meters per second. From here, now this becomes much more familiar. You can now solve for theta and the resultant velocity vector, so to speak, using vector equations or your known vector equations. Recall that for the resultant values is equal to the square root of the sums of the square of its x and y component. Substituting the values, you would get 42.72 meters per second squared. To get the angle or the direction, its polar coordinates, you simply get the tangent inverse of the y of the rise over run. I'm sorry, of the y. You simply get the tangent inverse of the y component over the x component, which would give you 20.56 degrees. If I recall it right, it's negative, so it's going to go clockwise. So that's 20.56 degrees south of east. For the last problem, we're here to identify the x and y coordinates. Recall the equation for the vector quantities for 2 dimensions as such. And also recall that your total displacement is simply the pxi times t plus half of axt squared. We simply substitute the values to get equations 1 and 2, and then we substitute it to the expression, to the known expression above here, and you would yield an answer here. This is your x and y coordinate represented as such at any given time t. So as you can observe, the velocity vector and the resultant, um, the x and y coordinate, are simplified with respect to time, so that when you're asked what is the position of both units at a particular time t, you would be able to just substitute the value t and be able to give a concrete answer for both x and y components. Okay. Last but not least, we have an example of a projectile problem. So this one is simply a long jumper. Okay, we're given a long jumper, and he or she leaves the ground at an angle of 20 degrees above the horizontal, and at a speed of 11.0 meters per second. It's actually fast. We're being asked what is the how far he jumped in the horizontal direction, aka range. You could also say that's your final position is being asked from its initial jumping point. And B, what is its max height or H max? Recall the equations that for to get your range, you simply use this formula here and substitute your given, you would get 7.936 meters. Mm-hmm. And to get the maximum height, you simply substitute the formula, uh, square of initial velocity and the square of sine theta over twice the acceleration due to gravity, and you will yield at 0.722 meters above the ground. There you go.